At the same time, Ralf Kötter was working on that, and they also looked into which packet to code together. So our question was always, should we code packets together that only a few members have it, or should we code packets in that everybody has? So when you code in packet that everybody has, it's easier to take something out. It's easier. But on the other side, you also have to do something to make everybody happy. So there was a question how to do this, and there is something essential to network coding. We need the marriage of coding and the protocols. As we are a communication network chair, we are very good in protocols. And we have to understand now network coding. And once we understand also why protocols are so important. So this is a little bit cliffhanger for something where we show you in the end how protocols kick in and what is the impact of that. So in general, we have seen that XOR coding, this simple combination of packets, can do a great deal for the efficiency of the network, right? But when you have, for example, only 2 packets, what can you do with XOR? You can only combine them once and later. So I can send packet A, packet B, and XOR. Can I do anything more than that? So there is some very interesting work. It's called zigzag coding, right? And if I heard zigzag, I was always reminding a nice storyline as a kid. I think if you hear that, there was something called zigzag, right? And what is this zigzag coding? Imagine you have a base station and you have a large number of devices and you have only 2 packets, right? So you have packet A and B, and I already give you the bits in the packets, right? 101 and 001 for the packets. So what would the base station do to transport this information? So it will first send packet A, then packet B, and there are losses. So station 1 would say, I'm done, right? 2 will say, I have only 1 packet. Packet 3 said, I have only the second packet, and so on. Others don't even received anything yet. So what you can do is you create this XOR, the magic XOR. And how do you do this? So the decoding part is if you get these systematic packets, so the real packets, you don't have to do anything, right? Then you can say, I could even say, so he is done, the others are not done. Now I do my magic XOR, encoding XOR 101. You understand how this works. And then you send it out. Now, he has 2 packets, and these guys have only 1 packet. Here we have 2 packets again. So we are not done yet. What would be the next thing? So he will be happy. Station 2 will say, okay, I have 2, and we can show this decoding. I got the real packet and a combination, and then I can just clean this up and get it out. That we have done before with the butterfly. Easy. But what is the next that I could send? Now it becomes harder, right? There are not so many combinations. And there was a nice paper that said, okay, let's do a fancy trick, right? We create more of these packets. And what we're doing is we do the zigzag coding. So what we do is we keep 1 packet here and we shift the other 1 bit to the left. So don't think about packets of 3 bits, right? Think about packets of 1,500 bytes. And we shift it only 1 bit to the left. So what happens now is I'm coding XOR again. So this one is the first bit of the yellow one. This is the last bit of the blue one. And in between it's XOR. Anybody any idea how I will decode this later? So here's the decoding. So imagine there comes a coded packet, but you need also to understand not only now which packets have been encoded, you also need to know the shift. That has an impact on your encoding vector, right? We will not talk about this this time, but if you have packet B and you get one of the zigzag coding, now you have to know who was, this means B was shifted, right? So that is what happened before. So what we do is now to say, okay, it will look like this. How can you create this packet? What is the obvious thing? Well, you have the colors, right? So yellow is yellow, you just plug it in. And blue is here, right? So this is the simple reading of it. How do you get these? You just have to remember how it gets constructed, right? So to restore that, now we shift 1 the yellow to the 1 bit to the left again, and now we understand, okay, if we shift it here, how do we create this? So we don't look at this anymore, we just look at this. 0, 0 is fine. But what made this a 1? Oh, sorry, you can even take this one extra. So what made this a 1? So what made this a 1? So easy peasy, right? So this is a freaking easy trick to use XORs again. This means you have an infinite number of XORs bit from the base station for a small amount of packets. So the thing is, you could do that. Here's another example. What happens if you have one shifted and one XORed bit? Can you still repair this? So how will this work now? So what you see is this and this, right? So this you can just read out. Click, simple reading. But what is with the rest? Now you have to shift it a little bit, right? So this is not give, this and this give this. So what do you need here? A 1, right? And so on. Then you can, this and this gives this, 1 again, right? And then you can clean up this, and with this you can clean up this. So this is the zigzag, and this zigzag coding we need later for analog again. We just do it here in the digital space because I think it's way easier to understand what we are doing. You're reading from both ends and clean it up from both sides, right? Until you meet in the middle of the packet and you have something like this. Okay, so with that you can create, now you have the original packets, the original packet, an XOR packet, a shifted packet, and you can continue and continue like this, okay? Why we are doing this? Later, this is not really what but if it ever comes to you that you work on sensor networks, on very low cost device, then you will find out and say, hey, there was something they used which was primitive, but primitive means also low complex, and therefore you can deploy it wherever you want. So for the overhead considerations, as I said before, it's not only that you have to understand which packet was combined, you also have to say which packet was moved to the left or to the right. But it's up to you to define how you do that. It will make the overhead not so big, right? With 2 packets, you have 2 bits for the encoding vector, and for the shifting, depending how much you want to shift. Let's say if you have 1 byte, that's more than enough. So if you just have the simple shift, it's 1,500 byte and 2 bits for shift. Overhead is marginal. That is what we always say. Sometimes I think with this as a starting point, it's very easy for you to deploy it. You will get good results. If you really need to fight over these bits, you will find out a good way to make it even more efficient. So far we never needed it. So there are also different directions possible. It's not only that you have to go the lower to the left, you can even go to the right. You can have also more shifting bits, and I think we have an exercise for that prepared. So in summary, it's a very simple extension, but also powerful extension to the XOR world. The overhead is small, very low complexity. You could even achieve the same with Reed-Solomon and random linear network coding without overhead, but more complexity. We will show you this also later. And therefore, as I said, as an application field, IoT devices, low complex. Good.